Hello all. In today's video we're going to be discussing a new use for our understanding of the molarity. So this is a technique that we're going to use regularly when we're in the laboratory. A lot of times when you go into a stock room like we have downstairs, there's going to be bottles that are just laying around that have what's in the bottle, like hydrochloric acid or sulfuric acid or phosphoric acid. However, chemists, like I've said before, are lazy and we tend not to write out what the concentration is on that bottle. So that's a bad thing. We want to know exactly what the concentration is in order to figure out how this chemical is going to react in our different experiments. Another thing that can happen is if chemicals are sitting in a stockroom for an extended period of time, the concentration will actually decrease, or some of the solute will start decomposing and your concentration will change over time. So we want to have a technique, a way of going into an unknown solution such as the acid, hydrochloric acid, sulfuric acid, and be able to predict what the concentration is of that acid. And so this is known as acid-base titrations, and we use this a lot in general chemistry and analytical chemistry and organic chemistry. We use this a lot in the world of chemistry. So what is a titration? A titration is the concentration of one solution, generally it's going to be the base, is used to identify the concentration of a secondary solution. In most cases, it's usually going to be the acid. So how does this work? What types of techniques do we use? So in an acid-base titration, the standard solution of base. Generally, we use the base because the acids are the ones that kind of decompose, and we don't know a lot of times what their concentrations are. We want to make sure that we know them exactly at the time that we're using them, so we have to titrate them regularly. So bases are really easy to make. We can make a sodium hydroxide solution. We have very small pellets of solid sodium hydroxide. We can throw that into water, and then we can make a solution of a known concentration of base. So the standard solution of base is added slowly to a known volume of the acid. Now in the acid we're going to have put a type of indicator. There are lots and lots of types of indicators that are available to chemists. For acid-base titration, generally chemists will use the phenolphthalein. If you were in class last Thursday, you saw what phenolphthalein does. You've probably seen it in lab. It goes from a colorless solution in an acid medium. So if we had hydrochloric acid and we put phenolphthalein in it, it would stay colorless. The phenolphthalein will change colors and turn to bright pink when it's in a basic solution. And so at the point where it starts turning pink, we're going to call this titration, a titrated solution. Now, why in the world would we stop when this thing turns pink? So here's a picture of what our acid-base indicator looks like going from the start all the way to the end of a titration. You can see here we have a colorless solution. This is in the acidic medium. Here we have a glassware that's called a burette. We don't use burettes here at OU for general chemistry, but you will when you're in organic chemistry. So we're going to keep adding a base to this solution, to this colorless solution. This is the acid down here, until it starts to turn pink. Now, it's going to be a very light shade of pink once we eat away all of the acid, all of the moles of the acid solute. So what's happening is here we have moles of this acid. We have HCl moles floating around. When we add a base to that, the hydroxide from the base is going to react with the H plus from the acid, and it's going to form water. So we're going to keep adding base until all of those H pluses from that acid are eaten away by all of the OH minuses from the base. What ends up happening is once all those are gone, the solution is going to start turning basic. There's no more acid left. We've eaten it all away. And so the color starts changing because the phenolphthalein indicates when you're in a basic solution. So once we've eaten away all of the acid, the H plus from the acid, we're going to start changing this into a basic solution. And here we can start seeing the color change. Not very apparent, but it is a slight color change. If we keep adding base to this solution, what's going to happen is it's going to turn vibrant pink. and that's what we see over here. So we have the range of colors. What's generally going to happen is when you're doing a titration, you're going to want to stay in this color range. Being a titration is more kind of like an art form. It's mixing science and art together. If you're really good at seeing when things change colors, you're going to be pretty good at titrations. So we're going to call this our stopping point for the titration. If we go to this color, we've gone too far, and what's going to happen is when we back calculate the molarity of the acid, it's going to be too high. We're going to have assumed that we put in too many moles of this base, and then when we back calculate, it's not going to work. So this is the procedure in the laboratory. We're going to actually use calculations to determine, starting from the molarity and the volume of the base, going through a balanced chemical equation, calculating the moles of the acid. Now, once we know the moles of the acid, we already know what the volume of the acid solution was. So all we have to do is take the moles of acid and divide by the liter of the solution, and we get the molarity. So that's what the idea of the titration is. So let's see how this works. We have two different points that we're going to really talk about in this titration. The first one is the equivalence point. This is where the moles of H plus exactly react with every single mole of OH minus. So what that means is this is a completely neutral solution. It's at a pH of 7. All of the acidic components of the acid have been eaten away by all of the basic components of the base. The H plus is eaten away from the OH minus of the base. However, this is still considered a neutral solution, so our indicator doesn't really change. Here, you'll start seeing pink colors form a little bit at a time, but they'll disappear. So you'll add a drop, it'll turn pink, it'll go away. Add a drop, turn pink, go away. You're getting close to the equivalence point when the pink keeps disappearing. Now, once you're at your end point, which the end point occurs when all of the H plus is gone, and we've added in slight amount more of the OH minus in the solution, that's when the color is going to remain. And so we're going to get a color. This is overshooting, like I said on the previous slide, this is overshooting our endpoint. However, the color is going to remain. It's not going to disappear. So what we're going to do is we're going to want that pink color to stay for about 20 seconds, and then we're going to call that our equivalence point. That's where we're going to back calculate, because we'll know the exact amount of concentration of the base and the exact volume of the base that we've added. So if we had a balanced chemical equation, we can do some calculations.